Hello everyone, this is lecture 9 of PTRE 451545 Advanced Drilling Engineering. Last time we went through the YouTube model, we overviewed the YouTube model, how it works, and some basic uses of it, which will come handy later when we deal with well-controlled situations. Today we'll carry on. There is one item I want us to see, and then I can go over the first homework, which is due on Friday, 1 minute before midnight. The way Blackboard has it, I can only, the latest I can have you submitted in a day is like 1 minute before midnight, 11:59. They don't have it at exactly at midnight or 1 second before midnight. I don't know why. If I set it at 12 a.m., it's gonna be morning of that day. So I'll basically take 24 hours from you. So I make it 1 minute before midnight. That's the latest. It's considered end of the day. 11:59 is considered end of the day for Blackboard. But you already know how to do most of the homework, which is easy, in all honesty. Just one item that we're gonna see, and it's more about terminology. And it's terminology that is used in the industry, so I want you to be familiar with it as much as possible, so that you can make a good impression when you go out, maybe this summer or after you graduate in the industry. Okay, we did about MW calculations, we did about the YouTube model, and we stopped. We saw what it is, what it happens when you have two fluids on one of the legs of the YouTube model. The left leg indicates the inside the drill pipe, inside the drill string, and the right leg indicates the annulus. And you have surface pressures at the top of both legs, and you have bottom hole pressure between the legs, and under the legs you have the formation pore pressure. Now, to be in a balanced situation, you want BHP to equal FPP or be a little bit higher. But that's when you are basically within this mud window that we talked about. You want your mud weight to be between these two limits. If you are here, you don't have enough to hold the pressure of what you are drilling through, so you get a kick. If you are here, you have too much, and you fracture, you lose fluid, and then you end up here again because you lost fluid, less fluid in the well, and you get a kick. So both situations, if you don't do them right, it's gonna lead to a blowout. Now, what I was gonna say, oh yeah. Now this is BHP equals to FPP is a balanced condition. If you get a kick and you have to shut in the well, you force it to become at a balanced condition, so you get some values here. And that's basically what you cannot, the fluid that you have in the well cannot balance. It's the part that basically you are missing. If you had it, and we're going to go through this in more detail in module 4, but if you have been drilling correctly and you are doing it right, you can shut in the well, or even you don't need to shut in the well, you can stop pumping, just stop pumping, and everything will go to zero. There will be zero everywhere. That's an indication that you are doing everything correctly. Many times during drilling operation, they will stop because they think they have a kick, and they will just stop pumping, and they will see if they get backflow. And if they get 0-0, it will be fine. Now, in some geothermal wells, because they are drilling through hot formation, if you stop pumping, the heat of the rock will heat up the mud. The mud would expand, and you may get some backflow. That is not necessarily an indication of a kick, but it's still it's a concerning factor, because if you let it happen a lot of time, you will get a kick because you are removing mud from your well. But anyway, we're going to talk about kick indicators later on. Anyway, The next item I wanted us to check is the static fluid level. And there is a question on the homework about calculating the static fluid level. And it's, in all honesty, is nothing crazy. It's just a terminology thing. It refers to the depth, the true vertical depth at which the fluid in the wellbore balances out the formation pore pressure. It's given by this equation. And if it is possible that the static fluid, excuse me, the static fluid level is on the surface. At that point, the shut-in surface pressure is above zero. What I mean by that, let me draw a schematic, and I will do it. I want to show you what I try to draw here. I have a well. It's a hypothetical well, and it's filled with orange fluid. Okay, orange fluid of density rho mat. I don't care what density it is now, but the well is 10,000 feet. Trying to make some easy numbers. Okay. And the mat I have inside with this weight only requires 8,000 feet to be filled. If I have orange mat of 8,000 feet, the bottom hole pressure here, which is calculated by 0.052 times rho mat times 8,000 feet, would be equal to the formation pore pressure, what I'm trying to drill through. Okay, say that the rho mat is 9.62 ppg. 9.62 times 0.052 is 0.5 times 8,000 is 4,000 psi. Say that FPP is 4,000 psi. I don't need the whole well filled with mud to balance this 4,000 psi, right? I only need 8,000 feet. So the static fluid level, I say, is on the 2,000 feet from the surface. Yeah, and I put the comma wrong here. It's 10,000 feet, not 1,000 feet. I guess I need to have, yeah, this is a mistake here. Sorry, 10,000 feet. So I don't need the whole well filled with mud to balance the formation pore pressure. I only need 8,000 feet. So my static fluid level is 2,000 feet from the surface or 8,000 feet from the bottom hole, right? Just a hypothetical scenario here. Now let's assume I do not have, or let's assume that the bottom hole pressure, sorry, the formation pore pressure is 5,000 feet. Then my mud, which is 9.62 times 0.052, 0.5 times 10,000, then I need to have the whole well exactly filled with mud to balance the 5,000 feet formation pore pressure, right? Okay, where is the static fluid level then?
At the surface.
At the surface. Okay. Very nice. Very good. What if it's bigger than 5,000 feet? What if it's 6,000 feet? Oh, sorry. What if it's 6,000 psi? I can have the whole well filled with fluid. It's not enough to satisfy the FPP, right? I can have the entire well filled with mud. The best I can do is 5,000 psi. If this is at the bottom hole pressure. If this here is 6,000 psi, I'm missing 1,000, right? That means if I shut in the well, what would be my surface pressure? Exactly 1,000. So where is the static fluid level in that case?
It should be 12,000 feet.
Above. Okay, above the surface. In that case, you're going to say the surface fluid, the static fluid level is on the surface. That's the convention that we use.
Can you come again?
Yeah.
If we get our height to be 12,000 feet, which is above the well, so
Yeah.
what would be the answer in such situation?
We will say static fluid level is on the surface. You will say 12,000 feet. You will calculate minus 2,000, right?
Mhm.
You have 2,000 above.
Mhm.
It's a hypothetical level.
2,000 above.
Yeah, correct. The correct answer is that the static fluid level is on the surface. Yeah. So same with zero. This is the convention use, basically. So example problem number 6, I think it's very similar to what we have been discussing. A well is drilled 10,000 feet down to an oil-bearing sand zone of 5,000 psi formation pore pressure. So it should be a vertical well. Calculate the BHP and static fluid level if the well was drilled with 10 ppg mud. So I need to draw the well, not very difficult task. It's a 10,000 feet. Is drilled with this, let's make it pink, I guess, mud weight of raw mud of 10 ppg. Calculate the BHP. And you also know that FPP is 5,000 psi. So what is the BHP? BHP is the weight of the mud. It would be, I think I have the answer written, but very easy calculation. Maybe I need to remove. Anyway, what it says is that it's 0.052 times 10 ppg times 10,000 feet, which is the vertical depth. The answer is 5,200 psi. Now, I am bigger than the FPP by 200 psi. I'm 200 psi over pressure, right? Because the FPP is 5,000. I have 5,200. So it's good. I'm above. I'm balanced. Over balanced, in fact. I hope I'm not too over balanced. The static fluid level would be 5,000 divided by 0.052 times 10. That's the equation from the previous slide. And basically, you are going to say is 96.15 from the bottom hole? Or what would that be? 375 feet from the surface? Always use a reference. So basically, it's below the surface. Static fluid level is somewhere here, right? Very, very simple. Example problem number 7. Same well as in example problem number 1. But the well is drilled with an 8 ppg mud. I think I wanted to say here number 6. Yeah. Example problem number 6. Yeah. Sorry about that. I need to make another change in the slide, so I will make this as well, and I will make sure the previous problem says vertical well. What else? There is also another issue with one of the slides in the animations. I will fix that too. So I was gonna do it last night and I forgot. Okay, so same well again. 10,000 feet, TVD, something like that. We know FPP is 5,000 psi, and we know the mud now is less. I will make it yellow. Is raw mud is 8 ppg. Okay. So to calculate the bottom hole pressure here, BHP question mark, is 0.052 times 8 times 10,000, which is whatever.
I think it'd be 4,000.
it would be, yes, it would be smaller than 5,000 for sure. 4160, if I did it correctly. That means I'm missing 840 psi. Okay, if I shut in the well, what am I going to be reading on the surface? Exactly, 840 psi. Now, what is the static fluid level? Is 5,000 divided by 0.052 times 8 ppg. And you will calculate something that is higher than the depth of the well, right? 12,000. In that case, it would be you will say on the surface. You see, it's written here on the surface. This is what you should calculate the number. Now you can rearrange this static fluid level equation and make it such that it gives you the depth from the surface. In that case, you are going to do something like 5,000 minus 4160 divided by this, and you are going to get something like if you do it 4160 minus 5,000 divided by this, you are going to get minus 2019, something like that, which is also an indication that you are 2,000 feet above the surface. That's something like unnatural, right? You understand that is non-physical answer, right? So basically it tells you I don't have enough math. I don't have
minus 2019.
Yeah, exactly. That's what you are missing because the well is 10,000 feet. So you need a well that is 12,019 feet to hold this pressure. You need a 2,000 feet, 2019 feet deeper well to hold with this mud. So basically it tells you your mud is not heavy enough. You are in the left side of the mud window. That's what you need really for the homework. It's just for the static fluid level, that question. Before we go there, let me just overview the homework for you guys very quickly. Here, question number 1 for 5 points. A vertical well is 10,000 feet through vertical depth and is completely filled with salt water. The static surface pressure is 0 and static bottom hole pressure is 5,000 psi. Calculate the salt water density in ppg. Note, the fresh water has 8.33 ppg density, which translates to 0.433 psi per foot. You know what I'm trying to give you with this?
I did 0.5, they're just trying to.
Yeah. In the exam, this is how it's going to be. I'm not giving you 0.052, but I'm giving you, if you take this and you divide by this, it's 0.052. Okay, so we said you have depth, you have pressure, bottom hole pressure, and you need to find the density. So you have 2 of the 3, you need to find the third. It's a very easy question for 5 points. It should take you 2 minutes.
1 second.
Huh?
1 second.
Yeah, very easy. Second question for 15 points, 3 sections of 5 points each. The formation pore pressure in a fluid-bearing sand at 15,000 feet TVD is 7,500 psi. Where would the static fluid level be? Defined as the level to which the fluid rises in a well when the well is shut in. It is known as the hydrostatic head of the fluid, which is equal to the well's BHP. That's the official explanation of static fluid level, if at all. And what would be the static shut-in pressure at the surface if the formation fluid is A, salt water of 9.6 ppg, B, oil of 30 degrees API gravity, and C, the formation fluid which honors the approximation P2 equals P1, 1 plus 25 delta TVD divided by 1 million, where delta TVD represents a change in the TVD in feet, while P1 and P2 represents the pressure in PSI across this delta TVD. Okay. Basically, it's asking for a static fluid level. But for section A, I'm giving you the density. That becomes basically the easy like the first question. The second one, I'm not giving you the density, I'm giving you API gravity. You can convert that to specific gravity and then multiply that by the density of water, fresh water, which is 8.33, and you get the density in ppg. For the C, it's a little bit more complicated, but not terrible. You are given, let's see, you are given the two pressures. Can I write here? Yeah. Okay. You are given two pressures and then the change in delta TVD. So if you know one, you can find another one.
Yeah.
So it can be translated to that very easily. And from the pressures, you can get the TVD. Remember, you are looking at the static fluid level. The pressure is balanced, right? You have enough height, as in delta TVD, to balance the formation port pressure, right?
Can you go again, sir?
Yeah.
Your explanation now.
Yeah. So you have this correlation, right?
Mm-hmm.
Okay. And I basically need to, there are three unknowns. I want you to input two unknowns and get the third one. You want the pressure at the bottom to match the FPP, right? BHP to be equal to FPP. You know this.
Mm-hmm.
You also know this, but you want the static fluid level, which can be in between.
Anywhere.
Yeah. So this is what you need to use, this equation. It can be confusing, but it's just basically one correlation.
Won't that lead us to two equations in mathematics?
No, I think I can do it with one in my head, but no, one equation.
I think. Well, I tried two, and then one, and this morning I tried one, and I think I was arriving the same.
We have more than
Okay, let me give you a
one
hint.
unknown. So
Well, I cannot make it that simple, but if the pressure on the surface cannot be zero, what does that mean about static fluid level?
that means it is above.
Huh?
That means it is above the well.
Okay, what does that mean?
That means the bottom of flowing is less than the formation port pressure.
Okay, yeah. And what is this correlation really for?
What is it for?
What is it for? We saw that in the slides. What is this correlation for? It's for
Predicting
what kind of fluids is
It's
this?
I think if we empirical studies something.
Yeah, but what kind of fluid? Like
is it static or dynamic?
no. What kind of fluid? Like is it what phase do you expect to see that?
Gas.
Okay, gas. Okay. Do you expect gas? Where do you expect the static fluid level for a gas to be really?
At the surface.
Always, right?
Yeah.
Okay, but you need to show it mathematically, and it's very, very simple. It is much simpler. If I have gas, the static fluid level will be on the surface because, I mean, I cannot get the pressure to be zero at any point. Like, if I said P2 equals to 7,500 PSI, I can use whatever delta TVD I want. It will be positive P1, right?
Mm-hmm.
Anything I can do. So that implies that I'm basically don't have enough to hold the mat. And this is really because gases are stored under pressure. They are going to be under pressure. That's why they are compressed. But yeah, I don't want to make it harder than what it really is. I think you guys have the answer already. Question number 3 for 10 points. A shut-in vertical well is drilled to 10,000 feet TVD and has been shut in, remaining filled with drilling fluid of unknown density. The static wellbore pressure is 3,598 psi at 5,000 feet TVD and 6,198 psi at 10,000 feet TVD. Calculate the mud weight in ppg and the shut-in drill pipe pressure at the surface. Now, for that question, you are given enough information to write 2 equations. Okay, 2 equations, 2 unknowns. Unknown is the mud weight, and what else? Yeah. So you might be able to do it with just 1 equation, but what I do normally to solve this is I know to go from 5,000 to 10,000, I gain this minus this PSR, which means how much the density should be to take me from there. Okay? And the other unknown would be, okay, imagine if I'm on the surface, what would be the pressure, basically? So imagine my whole well filled with that mud. What would be basically the pressure on the surface? It's actually a very easy question. A very easy question. Shut-in drill pipe pressure is basically what I have been asking you guys for what is the pressure on the surface. I assume there is only 1 fluid inside the well, so both legs will show equal pressure. That's why, yeah, we don't have a kick in these questions. Question number 4. A vertical well is 10,000 feet TVD, has been shut in and remains completely filled with salt water. The static surface pressure is 0, and the static bottom hole pressure is 5,000 psi. A, calculate the salt water density in ppg. Again, note the fresh water density is 8 ppg and translates to 0.433 psi per foot. So I give you again the 0.052 in case you forgot it from the first question. I give you 5,000 psi BHP, and I give you the depth. And I'm telling you the static surface pressure is 0, which implies that if I shut in the well, I'm going to be reading 0 on the surface. That means I have enough. Now, I cannot be reading negative on the surface. I can only be reading 0. If I have more than what I need, I will still be reading 0. Okay? So it's important. Those SICP and SIDPP that we were talking about in the previous lecture, they can only be positive or 0. Okay? You cannot have a vacuum there and read a negative value. Okay? Okay, what is the salt water density in ppg? Easy to find. 1 calculation, 1 equation. What is the shut-in casing pressure, i.e. the surface pressure on the annulus? Again, if I sort of give it away, but if I only have 1 fluid in my system, what I read on the drill pipe side, drill string side, I should be reading on the annulus as well. What is the pressure in the open hole at the casing shoe depth in PSI units? Give your answer in terms of DCSG. which is in feet. Now, you need to use the right side of the YouTube model and derive an equation for the DCSG. Now, you know, let's just make it here. Oh, there is chat. Somebody said pentane, natural gas. Oh, I guess it was when I was asking a question about the previous. Yeah. I don't mind writing on the chat. It's just if I'm not looking at the screen, I'm not gonna see it on time. But this. So sorry, Tito. Let's see. I have a YouTube model. Now, I'm lucky, the whole thing is filled with one fluid. So what I'm reading here, I should be reading here. It can be positive or it can be zero. My FPP is here, my BHP is here. And somebody told me about the DCSG. And what is the pressure in the open hole at the casing shoe depth? And in PSI units. Give your answer in terms of DCSG. So I want your answer to be like something times DCSG. DCSG will be the answer. Actually, drawing the YouTube model made it harder, made the question sound harder than what it really is. But that's the idea. I have a math of a certain way, then when you multiply some numbers, you give me the answer in DCSG. Now, when I say assume that DCSG is in feet units, it's because I want you to use that 0.052. Okay, that 0.052 has density in PPG, true vertical depth in feet. So DCSG is like a true vertical depth. That's why I want you to use that number. That's why I'm giving you that hint. Part B, what is the fracture pressure at the casing shoe, assuming 0.68 psi per foot fracture pressure gradient? Give your answer in terms of DCSG, which is in feet units. That's a little bit of a dumb question, but you will figure it out. It's very easy. Part E, the well is now shut in and 1000 psi are applied at the drill pipe. Assuming the system is incompressible, calculate the BHP, the surface pressure on the annulus, the pressure at 5000 feet TBD inside the drill pipe, the pressure at 1000, at 5000 TBD in the annulus. Now, everything is the same, but I have 1000 feet PSI on the surface extra. That means I need to go and adjust accordingly. What do you think happens if you have 1000 PSI on the surface extra? What happens in the YouTube system?
That means there's probably a kick or
No. I'm applying them. It's on the drill pipe side. I'm applying them. I'm pumping or something. Somehow I apply 1000 feet PSI. What does it do to my system, to my mud system? It should impact everything.
yes.
By that amount. Okay. Now assume that the top, question number 5. Assume that the top half of the annulus in the well from question 4 is filled with gas, which can be assumed to be weightless. From the surface halfway down to 5000 feet TBD. The rest of the well is filled with the same salt residue, with the same salt water as in question number 4. The well is shut in and the surface drill pipe pressure is 1000. calculate all this stuff. Now, the question is saying, basically, draw a YouTube model it's 10,000 feet. And I have math. And then halfway through, yeah, I'm gonna, that gas is yellow. So it's like what we did in the YouTube model. The thing is that that gas is weightless. It's assuming that doesn't have any weight. So 0. It's even easier, like for you. You don't need to add anything. In the I-, you only have half of it filled with purple, the matte. Okay? And okay, you already calculated the salt water density before, so you know it. And I'm asking you to give me the pressure at different points. Like give me the pressure at BHP, okay? 2 ways you can do it. But you have information to do it only with 1 way. The pressure at 5,000 feet in the diameter, so the pressure, can I write the pressure here? 5,000 feet. You use the YouTube model for that. The SICP, which is the pressure here. The minimum DCSG necessary to prevent fracturing, assuming a fracture gradient of 0.8 ppg, psi per foot, sorry. Hint, DCSG is less than 5,000 feet. You should never let the pressure in the annulus extend, exceed the fracture pressure at that depth. So I'm giving you a hint here that my casing shoe is less than 5,000 feet. So it's somewhere here, DCSG. I want you to, what did I should have used orange. Sorry about that. Okay. Now, I know the pressure here. And I know the pressure here. I want to write an equation where DCSG is the unknown and the pressure of DCSG times the frac gradient would be basically equal to the pressure here. So I'm barely making. So if I want to be just at the point of fracture and my fracture gradient is 0.8 psi per foot, my fracture pressure here at the casing shoe needs to be 0.8 times DCSG. Okay, I want my fracture pressure to be 0.8 times DCSG. So I need to get here somehow in the YouTube model, either from here down, if I have good information, or from here up. Right? Now, the thing is that this problem, yellow is weightless. So I start from here and I remove weight, I make it here. And then there is no way to remove until I make it here, which is the surface pressure. So I know the pressure here, and I know the pressure here. And there is no difference between the pressure of the yellow. It doesn't add any weight. The yellow is weightless. So if I make it here and say it's X PSI, it will be X PSI all the way here, right? Which is basically the surface pressure. So I need to write an equation with one unknown, DCSG, and then solve for it using the YouTube model. And I think it's easier to go bottom up than top down in that case. But maybe you can.
What you're saying is if I get to that from bottom up, if I get to that 5,000 feet where I have mud, the pressure there should be equals to what I have from there up to the surface. Is that what you're saying?
Yeah, you mean that the pressure here is the same as the pressure here? Yeah. Why is the case? Because if I have surface pressure X, and then the next fluid that I have fluid that doesn't weigh anything until 5,000 feet. So I go to 5,000 feet, and my pressure is still X. So my pressure here is still X. Okay? And then I have the purple fluid that weighs to go down. Okay? So it's that yellow fluid is as if it's not there, hydrostatic wise. It's like it doesn't exist. It doesn't weigh anything. It's ether. You know, it's basically it doesn't weigh anything. I ignore it. So if my pressure here is X, my pressure here would be X. And then I have X plus, plus until I make it to bottom hole pressure, which should be equal to the formation point pressure because I need to be at standard at balance conditions. So it would be an easy equation if I know FPP. If I know the pressure here, I basically need to set this pressure. If I know the pressure here, what is the difference between the pressure here and the pressure here?
That should be equal to you multiply 0.05 times the density.
But we said the yellow is weightless.
But won't you use the density of the mat?
The density of the mud is below.
Below?
I used it to get here. And then the pressure here versus the pressure here, what is the difference?
The difference should be that 0.05 times the density times 5,000 minus 3,000.
There is no density, it's the same. There is no density, we said it's weightless. So the pressure here is the same as the pressure here. So you just need to find the pressure here and say that pressure here is equal to the fracture pressure here. And what is the fracture pressure here? Is 0.8 times dCSG. One unknown, dCSG. You find the pressure here, and that is the same as the pressure. I don't understand why. I get so many texts from telemarketers. The same pressure here is the same as the pressure here because yellow doesn't weigh anything at all. And I want the pressure at the dCSG to be equal to the fracture pressure at dCSG, which is 0.8 dCSG. And therefore, I solve it basically. It's a simple equation if you use the YouTube model. Start from the bottom and go up. Remove the weight for 5,000, hydrostatic weight for 5,000 feet of salt water, purple salt water, and get the value there, say it equal to 0.8, and yeah, easy. Now, the last point is a little bit more difficult in the sense that I'm telling you that I have a different mud weight, fracture pressure, excuse me, and it's something like, is in between, oops, sorry. Let me draw. This is all yellow. Yellow doesn't weigh anything. dCSG now is here. Here. Is below the yellow. So I need to say that, forget about this, the pressure here must be equal to the fracture pressure there, which is 0.68 times dCSG. But what do I have here? I have, what do I have above me? I have surface pressure plus this little bit of purple, right? this little bit of purple. By the way, I can do it both ways. I can go top, bottom, or bottom up. And you guys need to figure out what's the best way you can go. You can only go one way based on the available information. That's the situation. But you have to calculate the pressure here mathematically and set it equal to the fractional pressure, which is 0.68 dCSG. It's basically an algebraic equation, one equation, one unknown. That's all you need. Very easy. Simple.
Can I quickly ask a question? For the first one, then the pressure we should have the pressure here will be equal to the pressure. To get the pressure here, do we need to consider the surface for the first one, or we don't need it?
Well, don't you think, what do you think would be the pressure there in relation to the pressure of the surface?
It should be this plus, in actual sense, it should be whatever we have here plus, you assuming the weight, the gas has a weight plus the.
But we said the gas doesn't have a weight.
So it will be this plus the 0.8 times G.
No. The pressure here, if the pressure of the surface is X, and everything to that point I'm looking for is weightless, the pressure at that point would be X.
Yes.
Because I add, it's X plus 0. I add nothing basically, right? Okay. Now, I need to set it up such that X is equal to the fractional pressure at that point, or X plus 0 in this, right? Okay, here. I know X fractional pressure is 0.8 dCSG. So I need to do X equals to 0.8 dCSG. If I know X, I can figure it out. I mean, don't I know X already? Do I know X already by that point in that question? Have I already calculated X?
Yes.
Yeah, you covered that as a SIC.
Exactly, yeah, what he said.
Yeah.
You did it on part B, part C, whatever,
That's 35.
right?
So that's all.
Pretty much. But the bottom point is like a little bit harder. Part B is a little bit harder because you have this section of purple which weighs. It's like it weighs. It's like I have X plus. It's no longer plus 0. It's plus this much weight of purple equal to 0.68 dCSG. Again, one equation, one unknown, but a harder equation, right? Mm-hmm. On the right-hand side of the equation, it will be longer, a little bit more complex. That's why I get the fractional gradient lower to be able to allow for that. But it's not hard. It's very easy to do. Yeah. Any questions? Okay. Let me know if you do have any. We still have Thursday's lecture too before the homework is due. So, and I have office hours today, but I mean, if you find me in my office, it doesn't have to be office hours. Now, for the online people, they don't have this luxury. I have office hours 1 to 4 today. But if you really have something, a question coming up, or I mean, you can email me, and so do the on-campus students, or you can email the TA. He knows all this stuff very well, and can help you. So that about the homework. I need to make some fixing in the slides. Now we'll carry on to the well-controlled system, which is the system that we haven't talked about a lot in modules so far. Okay, it's the 5th system in ERIC, and it's a very important one. It involves several components, like the BOPs, which are usually colored red. Oh wait, I have something else on the chat. Somebody said 0. Yeah, that's probably an answer to a previous question. Okay, these are the BOPs. Okay, they are below the rig floor, the dirty place to be. They are usually colored red. They are very important. They need to have a certain configuration. You decide on what kind of configuration you want it to have. Oh, sorry, I have the thing hanging here. Let me move it. Now they are operated. This is what you use to shut in the well. When I said the well is shut in, you use the BOPs to shut it in. You applied high pressure on those rams and you close the well. Now the pressure of the rams is basically coming high pressure nitrogen. Okay, they usually have the bottles of the nitrogen away from the well, so you can access them if the well is on fire, if the rig is on fire. So it's a little bit far away, and they are connected. And there is also another remote control panel really further away that you can access it in case everything is on fire in the vicinity of the well. And there, basically, it should be the last man standing. The whole rig can melt down. The blowout preventers are the last ones to go. It's very important. They are regularly tested. They follow protocol in the way they are tested and how often, the frequency at which they are tested. And like I said, there are several types of blowout preventers, of rams, and the operator decides on what configuration we have. Do you want 3 pipe rams and 1 shear ram? Do you want a blind ram and 2 shear rams and then a pipe? I mean, you can arrange them a certain way, any way you want. And obviously, you're not going to do it randomly. You are going to do it with advice from whoever sells you the BOP. The first BOP was invented in the 20s by Cameron and Abercrombie. Cameron of the Cameron that SLB owns now, I think. Anyway, so this is a basic, very basic schematic of the blowout prevention system. The shut-in of the well is necessary when hydraulic control is lost. That's basically when you have a kick. When the pressure of the underground fluids is greater than that of the bottom hole mud well. That means what I'm trying to say here with a lot of words is simply this. Now that you guys know, my BHP is not enough to hold. I have kick. I need to shut in the well. This is what I'm going to use, the BOPs, and hopefully I will prevent a blowout. That is their function, blowout preventers. They prevent blowouts. BOPs consist of a series of valves installed on the top of the wellhead that prevents fluids from escaping. It can basically hold pressure. So the wellhead and the safety equipment are the valve units that allow the well to be insulated from the outside environment. In this way, it is possible to control effectively and safely the pressures that develop in the well when it is in hydraulic communication with the subsurface formations. So when you are drilling, if you don't have casing yet, or you haven't set up casing, you are really interacting with the formations you are drilling through. That's why I say BHP must be equal to FPP. Otherwise, I get fluids from the formation into the well. That's basically a kick. The wellhead is fixed. It's a fixed unit that connects the various casings or casing strings set inside the well. So this is where they all anchor. We said casing, make it all the way to the surface. So where do they anchor on the surface? On the wellhead. Okay, the BOPs are above the wellhead. They are installed on the wellhead. Remember, there is always a wellhead from the drilling until the production. It's just During drilling, we call it BOP, basically BOPs. During cementing, it's a cementing head on top of the BOP, but that's considered basically to be on top of the wellhead. When you fracture, there is a frac tree. And when you produce, it's a Christmas tree. Okay? They are all on the wellhead, basically, installed on the wellhead. That's what you see on the surface. If it is a producing well, this unit remains there until the end of drilling and is completed with a production head or Christmas tree. Production head and Christmas tree are basically the same thing. This is a BOP. Now, once you become experienced and they take you to a well and you see a BOP that looks like this, you will be able to deduce from the shape that this is basically the annular preventer or hydride. It's basically a balloon that inflates and covers everything outside of the pipe. This is the one they use more often. If you watch the movie Deepwater Horizon, they show the balloon breaking at some point.
Macondo.
That is basically the annular preventer. Some people call it the hydride. I think hydride was the name of the first company that made it or something. That's why this is the one that you use more often. And that's the one you can replace more cheaper. It's just a balloon that covers everything outside of the pipe. This stuff here, I don't know which is which. I can't tell which is which, but they're either blind ram, shear ram, or pipe ram. Pipe ram is just a piece of metal that closes around the outside of a pipe. But it needs to be a certain size. You need to know what kind of pipe you have there to close properly. If you have a joint, you are in trouble because the joint is thicker than the pipe, right? It can. Basically, if your drill string is basically like this, tubular, joint, tubular, joint, tubular. Okay, if your pipe ram is for this side, same thing here. If the tubular is, if the pipe ram is for this size, and you have this size, you are in trouble. This is the reason why people, when they shut the well, they generally raise the drill string before they shut the well until they see a tool joint right here above the BOP. If you see a tool joint here, the next one is located 30 feet below. That means you don't have anything inside. There is also another reason why they raise the drill string. You don't want the bit to be touching the floor, the bottom, when you are going to shut the well, because then it might be hard, you might get stuck. So you want to lift it. It's a good process, like always. You lift off the bottom and then you shut in the well. But you generally lift until you see the first tool joint. Then you know, okay, I'm safe inside. I don't have a tool joint in my BOP. I can use whatever ram I want. Okay. Shear ram cuts the pipe. That's the one they tried to use in Macondo, and basically it was worn down and then it couldn't do the job. They used it improperly. The blind ram doesn't care what you have inside, it just like seals everything. These days you have the blind shear ram, which basically do what these two do at the same time. It cuts and closes on top. That's the more modern version of ram. And we'll see shapes, don't worry. Now here, this is another ram. But here you have two lines, okay? If you look at the lines, one is thicker inside than the other. Because one is for producing, the other one is for injecting. Well, one is for circulating out, and one is for circulating in. That means injecting. The one that you inject needs to hold higher pressure. The one that is the thinner one, let's just say this is this one. I don't know, but let's just say it's this one, is the choke line. That's the one with the thinner walls. Right? And this one here, and again, I don't know if it's this one, but I'm just making, is the kill line. That's what you're gonna use if you want to inject something. Okay, it has thicker walls to hold pressure. If you go to Dracola, which thank God it doesn't belong to our department anymore.
Who owns it now?
It's okay. It's not. It belongs to the college. It has a lot of other stuff. It's called drilling and completions lab, but it's not. It has like an air tunnel in it. It has a robotics part in it. It has a lot of stuff that are not related to. Yeah, so it's not. Anyway, there is a BOP that was donated by neighbors. No, by a company, I don't know. And it's a part of a BOP, it's not an entire BOP. But you can see the pipe on either side, and one side is thicker than the other. You can really tell from there which side is the kill line and which side is the choke line. If you go and see, that thing is on the ground floor, on the basement. I brought my parents, I made them a tour this summer. I didn't get to the basement, but there is last time I was there for the labs in the summer, earlier in the summer, June, they were, I did see the BOP there, it was still there. You can really tell which side is which very easily if you see. It's like this part here, you see the hole, one is bigger than the other. The one that is smaller is the one that can hold higher pressure. So if you want to inject something down hole, you need to do it at a pressure. So you need to hammer the pressure. If you are choking, like the choke line, it's like you are removing something, you are circulating out of the hole, it's coming out at a lower pressure. It's just like the mat return line, but now the well is shut in. That's why I said SICP, you are measuring it from there. You are measuring the choke line, right? Got questions? No. Okay. And we're gonna see more pictures of that will make it clearer. Oops. Yeah, sometimes in some rigs offshore, you have a wet tree that is at the bottom of the ocean. Sometimes it's a dry tree at the rig floor. Sometimes you have two. Generally, well, Macondo was a deep water well, 5,100 feet. It was at the bottom of the ocean.
The BOP?
Yeah. It was damaged, and then they had to install something on top of the damaged BOP. It was very hard to do because it was down 5,000 feet. The safety equipment known as the blowout preventers are large valves located on the wellhead during drilling operations, able to fully shut in the well, in case of need, that is well control situation or loss of well control. BOPs on onshore rigs and fixed offshore rigs are installed on surface wellhead, while for floating rigs, because they are moving, you don't want to do it on the well, you want to do it on the sea floor because there is a range of motion you need to make to be able to make. So the marine riser that is between this is what you see, the riser, is the marine riser, is allowed to move. So you don't want it to be on the surface, you want it to be on the seabed. Mat floor, the sea floor in drilling, they call it mat line. That means the sea floor. Safety equipment. A standard BOP stack consists of, starting from below, one or more spools for connection to the wellhead. Okay, that's where you connect the BOP. Ram preventers, that's what we talked about, blind shear pipe, blind shear combined as well, a lot of stuff. An angular blowout preventer, also known as hydrille or angular ram, that's the balloon. A number of lateral connections, kill line and choke line, necessary for operations to restore hydraulic balance after well control issues. The BOP stack has the following functions: shut in the well around any type of equipment, permit pumping of the mat with the well closed by the kill line. So yes, I shut in the well, but I want to be able to circulate, not at drilling, not like when I'm drilling, maybe at a slower, it would be at a slower rate, but I want to be able to circulate, right? I need to inject and produce fluid, inject, let mat go in and have mat go out. To circulate the fluids that I got in out, it's gonna be done through the BOP, with the BOP closed. Okay, it allows it to do that. Discharge through the choke line any fluids that might have accidentally entered the well, that's kick fluids. Also, it's not common, but you want to allow vertical movement of the string upwards and downwards. This is not gonna happen like very easily. It's called stripping. And remember remember that little drawing I made with the joints and the pipe rams, like this? What's the distance from one joint to another? 30 feet? 31, something like that, okay. Now we said I have the pipe ram, it can hold here. Yeah. And then I have another pipe ram in the BOP, it holds here. Maybe, right? Then how do I strip in? I need to open this pipe ram or the other way. I need to open one of the pipe rams, move everything down, then close one, open the other, close the other, open the, like to get the joint through. If I want to get the joint down below this, I need to open this, then I need to have this closed. Then if I want to get this joint through, I need to open this, I need to have this closed. Because the pipe can strip through a closed pipe ram. It will happen slowly, there is friction, etc. But the joint won't. So I need to have that pipe ram open. But in order to have the well shut in, I need to have another pump ram higher up closed. That's why you see a lot of rams in the BOP stack, for instance. Right? If I want to pass it through, that's why you have. I might be wrong, but I bet you that, oops, sorry. For instance, this one here might be a pipe ram. Then one of these must be a pipe ram too. So if the tool joint is here, and it needs to go through this to go down, I need to open this pipe ram. If I have this open and this open, I lose control of the well. It's no longer shut in. I need to have one pipe ram closed, open one, and then move the joint through, and then close that one, open the other one on top to move the joint through. It's a slow, painful process. But I mean, it's a well-controlled situation. It's emergency. That's why you need the BOPs. So they need to be able to allow this function of stripping in. This is another schematic. It's kind of better because you see a lot of stuff. You see the kill line, the choke line. Oops, sorry. You see the kill line, choke line, ram. Ram. It comes in on its own. Okay, not touching it. Okay, you have blind ram, shear ram, mat returns line. That's where in normal drilling operations, the mat returns line is carrying mud out of the well at atmospheric pressure. At shutting conditions, you take mud out from choke at a pressure, SICP, right? So let me write here. If I am not true, if I'm shading, I take mud goes in, and then comes out through, mud goes in through SIDPP, comes out through SICP. Okay, if I am at open conditions, not shading, no shading at all, mud goes in through SPP or drill pipe pressure, and it comes out through mud returns atmospheric pressure. That's the long line that goes through the mud returns and it's open to the atmosphere. That's normal drilling operations. Now, I have the high trial. It looks like I told you guys, the balloon that closes on top of around the pipe, and this is how it looks like. The blue is the balloon. Look at how it closes, it wraps everything around the, it's like it's hiding the outside of the pipe. Doesn't let anything go through the outside. That's why it's called the annular preventer. It closes the annulus. Okay. Now, this is how the other ramps work, those stuff here. Oh, sorry. This is ridiculous with the touch screen. This stuff. Okay, and you have either this, or this. And this was a common Pedro ball schematic that they used in the past. And the way I remembered it, it was like alphabetical order. Blind, pipe, shear. Right? Okay. Blind closes on top of, doesn't care what it is there, but there needs to be nothing there. It should be empty space. Okay? So you're going to combine it with basically a shear or something. Or you need to cut everything, let it drop, and then close to basically safely. It's an emergency situation. I mean, you got to a point where you cannot save the drill string. You just cut it, let it drop, and then you close to shut it the well.
So,
okay? Yeah.
So the blind, does it cover, that one actually didn't cut the pipe?
No, it just covers. Now, blind shear, the modern day stuff, it does, it's this and this at the same time. So it cuts and closes.
But the closing, is it that it will just grip the side of the pipe? For those?
No, that would be the pipe. That would be the pipe.
It just grabs
the outside of the pipe.
The annulus,
yeah, that's the pipe. That's the pipe.
So that means a blowout can't happen through the pipe.
Yeah.
It can only be through the
Yeah, if it's in your drill string, you need to basically cut the drill string and then shut it. Or modern day, you have A and C together, it's gonna cut and shut at the same time. Most of the times now they use both. It's the blind shear runs.
The later is better.
Huh?
To be safe.
Yeah.
And cut.
Yeah. You cut and cover.
Maybe, but if you, that one will rather even cause also spoil your pipe. But the blind, maybe the kick might not be big
too
one,
severe.
too severe, and then you quickly.
But it's better to always be safe. And if you're alive, that's when you talk about money.
Yeah, but remember
that
the bit has nozzles.
Yeah.
The nozzles have very small diameter. So in most cases, where is the kick gonna go? The annulus or the drill string?
When you cut,
When you get a kick.
it passes through the annulus.
Yeah. Most of the times, or not always, it's gonna be at the annulus. So you care more about securing the annulus than the drill pipe. Although I have heard stories about old wells, the kick making it all the way through the drill string at the Kelly, all the way up, you know, in the drill string, which is, I mean, imagine to make it through the nozzles of the bit, you need a lot of pressure. But the nozzle may be broken as well. So, but yeah, I mean, most of the time, conventionally speaking, the not conventional operation, like more like common stuff, historically wise, it's gonna get into the angles. That's because of pressure. Okay, so you're gonna have the kick in the angles. In fact, if you do have kick getting into the drill string, you will need to either pump down and get it out from the annulus, or you can also do reverse circulation, but it's a long story. Reverse circulation is possible. You can inject from the annulus and get it out from the drill pipe, drill string. It's not impossible to do. We were doing exercises like that when I was in Texas about reverse circulation. Yeah, but most likely it's gonna be in the annulus. That's why a lot of stuff. I mean, the annular high drive is for the annulus. The pipe ramp is for the annulus. Yeah, I mean, if it gets to the drill string and it's coming up like that, I mean, must be a gas kick as well to be coming up to get you, because of the density difference. Yeah, I mean, you are in a very bad situation, but still can be managed. Anyway,
How is the kick? How is the kick line and the choke lines in terms of thickness? Which one is?
well, which one requires the higher pressure?
Well, when you look, it is the kill line because
Why?
you're pumping a lot of pressure down there to be able to kill
Yeah,
to counter the kick down there.
yeah, or you may be injecting chemicals from there.
Yeah.
So, which one do you think is going to have the thicker walls?
Yeah, to me, maybe the kill line.
You can use the kill line to produce in some situations. I mean, in Macondo, they tried to measure the pressure there. Well, they tried to do other stuff with the kill line there as well. But this is because they thought they had a pressure trapped somewhere. They were calling it the balloon effect. They had like pressure trapped somewhere, and they thought that their reading was wrong. So they should measure the pressure from another place so that they basically ignore that part where the pressure is trapped. And they got it wrong, obviously. And but I'm telling you that yeah, it's two lines, and you can basically, one is for injecting, the other one is for producing, and it directs to the choke. The choke is an important part. We're gonna see how, and because the choke is basically the mud exiting the well at a slow rate, and you can control the diameter it exits through. That means you control the SICP. You need to keep the SICP above a certain level to prevent more kick entering the well when you are doing kick circulation. You also need to keep the choke, the SICP below a certain level, not to get fracturing. Because if you get fracturing, you have what we call underground blowout, which is much worse than the surface blowout. And so you need to keep during the kick circulation, as we're going to see in module 4, the angular pressure between certain points, not high to frac, not low to get more kick. And just like the mud window. So you would manipulate that using the choke. The choke basically is the diameter at which the mud is moving out. And yeah, I mean, it's a very important piece of equipment. And yeah, we're gonna see next time. But you guys are ready to do the homework.
Yeah,
And-
when we have questions, we meet you early.
Yeah, I have class on Thursday. I have office hours this evening. I'm available anytime you need me. Just either email me or message me or swing by my office, and I will see you guys. Yeah, on Thursday. Thank you very much.
Yeah.
Thank you, Tito and Donald.
I want to see you briefly.
Huh?
Yeah, so I want to see you briefly.
Yeah. Recording.